Hydraulic pumps convert the mechanical energy of a prime mover, for example an electric motor, into fluid power or hydraulic energy. The pump creates flow, which determines the velocity at which components in the system operate. This flow and the pressure created by the system and its load determine how much work a system can do in a given period of time. The work a system can do is usually measured in horsepower. Industrial hydraulic systems use positive displacement pumps in which the output is the same for each revolution of the pump. As the pump turns, fluid is moved or displaced from an area of increasing volume to an area of decreasing volume. For example, the vane pump we have seen throughout this course creates an area of increasing volume on its suction side and an area of decreasing volume on its outlet side. Fluid is pushed into the pump by atmospheric pressure, then displaced from the pump as it turns. Three kinds of positive displacement pumps are commonly used in industrial hydraulic systems: the vane pump, the gear pump, and the piston pump. We'll examine how each one works, and we'll discuss how horsepower can be changed to match the work being done, thereby increasing the efficiency of the system. Let's examine the vane pump first. The vanes fit into the rotor and slide in and out as the rotor turns inside the ring. The ring, with its rotor and vanes, is sandwiched between the port plates which have holes or ports. Fluid moves through these holes, into the pump, and back out again. The entire package, all of this, is called a cartridge assembly, and it's encased in the pump housing. When this portion of the pump wears out, it can be repaired by simply replacing the whole cartridge assembly. And within certain limits, the pump volume can be increased or decreased by replacing the cartridge assembly with another one of larger or smaller volume, but with the same outside dimensions. Sometimes two cartridges are used in what is called a double pump. These pumps may have one or two inlets, but they will always have two outlets. The two cartridges that make up the pump may be the same, or they may differ in flow rate as well as in operating pressure. Since they are both mounted in the same housing and on the same shaft, they are driven by a single power source. Many industrial pumps have an elliptical cam ring. The shape of the ring provides space for two inlet ports and two outlet ports in the port plate. Since pressure from opposite ports balances the pressure on the rotor bearings, the bearings last much longer. Notice that although the port plate has two inlets and two outlets, the pump housing has just a single inlet and a single outlet. That's because the ports are connected together inside the pump. Industrial vane pumps generally have a minimum operating speed of about 600 RPM. This is the speed required for centrifugal force to sling the vanes out against the cam ring and form a seal that will start the pumping action. However, continued operation at normal hydraulic pressures requires a more positive seal. To achieve this, fluid pressure is directed to the underside of the vane, forcing the vane against the cam ring. However, as the system pressure rises, the force may be too great, and the vanes and cam ring may wear too much. To prevent excessive wear, pump manufacturers often bevel or chamfer the vanes, like this. The underside of the vane is fully exposed to system pressure. The top portion is only partially in contact with the cam ring, while this beveled area at the top edge of the vane is exposed to the same high pressure as the bottom of the vane. The opposing forces partially balance the vane. At relatively low pressures, these methods work well. At high pressures, however, several other vane construction methods are used. Each method reduces the loading on the vane as it moves along the surface of the cam ring. In one method, dual vanes are used. Each vane provides a seal, and each is chamfered on three sides, so system pressure almost balances the forces acting on the vane. Another method uses intravanes or pin vanes, in which system pressure controls the loading of the vane tip. Spring-loaded vanes depend on a spring underneath the vane as the primary means to hold the vane against the cam ring, although system pressure is also used. Another method of reducing vane tip loading is to position the vane at an angle to the cam ring. This method loads the top of the vane and offsets system pressure applied to the bottom of the vane. Changing the output of hydraulic pumps to match the workload and increase efficiency is sometimes done by changing the speed at which the pump is operated. Usually, though, it is less costly to vary the amount of fluid displaced each time the pump rotates. Let's take a close look at how the displacement of a pump can be varied to match the work being done. Consider the vane pump with the circular ring that we saw before. Pump flow can be changed by varying how far out from the rotor the vanes of the pump extend. Outlet pressure will be greater when the vanes extend farther out one side of the rotor than on the other. If the rotor is centered within the cam ring, there is no increase in volume between the vanes on the suction side, and no decrease in volume between the vanes on the outlet side. Therefore, no pumping will occur. However, if the cam ring is moved to one side, flow will increase until the pump produces maximum horsepower as the cam ring approaches the rotor. A variable volume pump has a movable cam ring and a means to adjust the ring. In this illustration, a screw is used to control the movement of the cam ring. In this position, with the screw backed all the way out, the cam ring centers itself around the rotor. Flow stops because there are no increasing or decreasing volumes created in the pump as the rotor spins. If the screw is advanced until the cam ring begins to move, vanes on one side of the rotor extend farther, while vanes on the other side extend less. As the cam ring is moved farther and farther off-center, flow increases. Finally, with the cam ring in its extreme position, the pump produces its maximum flow. Generally, variable volume pumps are also pressure compensated. This means flow from the pump will change as system pressure changes. This is accomplished by using a pressure compensating spring, which biases the pump's cam ring off-center. As system pressure rises, the force of the fluid pushes the cam ring back against the spring, reducing flow out of the pump as the cam ring moves towards center. The flow rate can be limited by adjusting a screw that prevents the cam ring from shifting beyond a predetermined position. Variable volume pressure compensated pumps must be externally drained to prevent buildup of fluid inside the housing. If excess fluid is not drained away, it will interfere with the pump performance. In addition, any leakage as the pump is compensating is generally very hot. Directing this fluid back to the inlet side would cause the pump to grow progressively hotter. External drains, commonly called case drains, prevent this from happening. Now let's look at the gear pump. These simple, economical pumps use two gears that turn and mesh inside a tightly fitting housing. There are two kinds, external gear pumps and internal gear pumps. The teeth of the external gear pump, often called a spur gear pump, take fluid from the pump inlet and carry it between the teeth and the housing, then discharge it through the outlet port. External gear pumps are also built with helical gears and with herringbone gears. The principle of operation is the same. Moving gears take fluid from the inlet port, carry it around the housing, and discharge it at the outlet port. External gear pumps are sometimes called gear-on-gear pumps. Internal gear pumps or gear-in-gear pumps are also available. One of the most common is the gerotor pump. The gerotor has an inner gear keyed to a shaft turned by a power source. The outer gear, which has one more tooth than the inner gear, is turned by the inner gear. As the two gears rotate, they create areas of increasing volume as the teeth move farther apart, and decreasing volume as the teeth move closer together. This creates inlet suction and outlet flow. Fluid moves in and out through a port plate, much like the port plate on a vane pump. The output volume of the pump can be changed by changing out the gears, but variable volume can only be obtained by changing the speed at which the gears rotate. The faster they turn, the greater the volume of fluid the pump produces. Typically, this is done with a variable speed motor. Earlier in this course, we looked at a simple piston pump with a single piston that produced a pulsating flow. In industry, piston pumps have several pistons, so they produce a relatively constant flow. There are two main kinds of piston pumps, the radial and the axial. The radial piston pump has pistons spaced around a cylinder barrel. As the pump turns, the pistons are extended by centrifugal force, by springs, and by fluid pressure. They ride along the cam ring on piston shoes. Fluid flows into a stationary valve block. On one side, the pistons move out, increasing the volume and drawing fluid into the pump. On the other side, the pistons move in, decreasing the volume and forcing the fluid out under pressure. Just as with the vane pump, the output can be varied by moving the cam ring. The axial piston pump also has pistons, but these fit into piston bores in a cylinder barrel. A shoe plate and a bias spring hold the piston shoes against a plate called a swash plate. The pump's inlet and outlet are through a port plate at one end. In operation, everything but the swash plate and the port plate rotate with the shaft. To understand how it works, let's follow the movement of just one piston during a single revolution of the pump. As the pump turns, the piston shoe rides on the swash plate and pulls the piston out of the bore. This creates an area of increasing volume inside the bore as the cylinder barrel rotates. Fluid is drawn into the piston bore through the inlet port in the stationary port plate. When the piston shoe reaches the top of the swash plate and starts down the other side, the volume in the piston bore gets smaller and fluid flows under pressure out through the stationary outlet port. Since there are several pistons, each in a different position at any one time, flow from the pump is very nearly steady. An axial pump can also be a variable volume pump. Varying the angle of the swash plate on an axial piston pump will change the output. The longer the stroke of the piston, the more volume the pump will produce during any revolution. Flow through an axial piston pump can also be reversed by tilting the swash plate beyond center. These kinds of pumps are called over-center axial piston pumps. Flow reversal occurs even though the pump shaft rotates in the same direction. Piston pumps can also be pressure compensated. Pressure compensation in an axial piston pump reduces pump flow when pressure reaches a predetermined level. The compensator mechanism consists of a spring-biased volume control piston, a spring-biased compensator spool, and an adjustable pilot valve. For example, in this illustration, the pump is producing 500 psi. The spring biasing the compensator spool in the spring chamber has a value of 100 psi, and the pilot valve is set to open at 700 psi. An orifice through the compensator spool to the spring chamber equalizes pressure on both sides. Now, suppose pressure from the pump rises to 600 psi. The spool remains non-passing because fluid pressure is the same on both sides of the spool. It is held in place by the 100 psi force of the spring. However, if system pressure rises to 700 psi, the pilot valve cracks open, limiting pressure in the spring chamber to 700 psi. Finally, at 800 psi, system pressure overcomes the combined value of the spring and the pressure in the spring chamber, 700 psi in this case. The compensator spool shifts, venting the control piston chamber to tank. When that happens, the force created by the pistons pushing against the swash plate overcomes the pressure biasing the control piston, and the swash plate centers, compensating the pump to minimum flow. As flow from the pump slows down, system pressure also drops, and the compensator spool shifts back, closing off the control piston chamber. Pumping action resumes. The pressure at which compensation occurs is controlled by the setting on the pilot valve and is equal to the combined value of the spring biasing the compensator spool and the setting on the valve. Many variable volume pumps are available with dual compensation. This means the pump can be compensated at two different pressures. This axial piston pump, for example, achieves dual compensation by using a solenoid valve and an auxiliary pilot valve. As long as the solenoid valve is closed, the pump compensates in the normal manner, just as we have seen. For example, if the main pilot valve is adjusted for 1300 psi and the spring in the compensator spool has a value of 200 psi, then the pump will be compensated at 1500 psi. However, the pressure at which compensation occurs can be changed by energizing the solenoid valve. Suppose, for example, that the auxiliary pilot valve is set for 400 psi. Energizing the solenoid valve connects the spring chamber of the compensator spool with the auxiliary pilot valve. Now the pump will be compensated at a pressure equal to the combined value of the spring in the compensator spool chamber, 200 psi, and the setting on the auxiliary pilot valve, 400 psi. The total is 600 psi. If the solenoid is de-energized, the pressure at which compensation occurs rises to 1500 psi again. When pressure-compensated pumps are used, hydraulic power is controlled by limiting pressure and by regulating flow. When pressure is closely matched to the work being done, and when flow is only as great as necessary for the speed at which the work must be done, then horsepower going into the system will most closely match horsepower going out of the system. This relationship between horsepower in and horsepower out is called efficiency. Usually it's expressed as a percentage. Efficiency can be calculated by dividing output horsepower by input horsepower. For example, if a prime mover like an electric motor must develop 100 horsepower in order for the pump to develop pressure and flow equal to 80 horsepower, then we say the efficiency of the system is 80%. This means that even in a well-maintained system, the input power requirement will always be higher than the power required for the work being done. In other words, efficiency will always be less than 100%. However, the efficiency of a system can very often be improved. Let's look at a system to see how that can be done. Suppose we need to move a cylinder to a workpiece quickly, then slow it down as the tooling feeds into the workpiece. This system requires a 50 GPM flow to rapidly advance the cylinder. When the cylinder rod hits the limit switch, it closes a solenoid valve and forces flow through a pressure-compensated flow control valve set for 3.7 GPM. This new flow rate slows the cylinder movement down to the required feed rate. The system's relief valve is set for 1500 psi. One way to get the required flow rate and pressure is to use a positive displacement pump designed to deliver 50 GPM at 1500 psi. To calculate the horsepower required, we can use the formula we learned in an earlier lesson. Multiply the flow, 50 GPM, times the pressure, 1500 psi, times the constant, 0.000583. The answer, 43.7 horsepower, is the power required of a system operating at 100% efficiency. However, suppose the feed portion of the cycle is 2/3 of the total cycle time. During this time, only 3.2 horsepower is required. This means that for 2/3 of the total cycle, most of the power, 40 horsepower, is being dumped back to tank. To increase efficiency, we can use a double pump in a high-low system like the one we saw in an earlier lesson. One side of the pump has a capacity of 45 GPM, and the other side has a capacity of 5 GPM. In addition, we will need to add an unloading valve. Both pumps together deliver the feed rate required for rapid advance. But when the feed portion of the cycle starts, pressure builds up and the unloading valve dumps 45 GPM back to tank at a very low pressure. Horsepower during the feed cycle is just 5 GPM times 1500 psi times 0.000583, or 4.4 horsepower, plus the horsepower required to dump the excess flow to tank. Even more efficiency can be achieved with a single pump, provided it is a pressure-compensated pump. Since the pump still has a 50 GPM capacity, it still gives the rapid advance required. However, when the feed portion of the cycle starts, the pump delivers only what is needed, 3.7 GPM. The horsepower delivered to the system is 3.7 GPM times 1500 psi times 0.000583, just 3.2 horsepower. Pumps with dual compensators can boost the efficiency of a system even more. For example, suppose the system we have just seen required an idle time after the feed portion of the cycle is complete. If the pump had a main pilot spring value of 200 psi and the pilot valve was adjusted for 1300 psi, then the pump would be fully compensated at 1500 psi, delivering just 3.7 GPM and 3.2 horsepower to the system. However, if the auxiliary pilot valve also has a 200 psi spring, then energizing the solenoid during the idle time between cycles will fully compensate the pump at just 400 psi. Horsepower will be 3.7 GPM times 400 psi times 0.000583, less than 1 horsepower delivered to the system. In this lesson, we have seen 3 of the most common hydraulic pumps used in industry, and we have seen how their operation can be matched to the work being done. In the next lesson, we'll take a close look at hydraulic motors.